And now we're going to look at how to predict the structure of covalent compounds based on the elements that are being combined in that covalent compound. So remember, a covalent bond is a bond between two atoms where they're sharing electrons. And so those electrons can be shared equally in a nonpolar covalent bond, or they can be shared unequally in a polar covalent bond. And bonds are formed, these covalent bonds are formed by the sharing of valence electrons. And so the whole thing we need to get started with is figuring out what valence electrons the atom has. So to do this, we'll look at what are called Lewis structures and how to make those Lewis structures. So a Lewis dot structure shows the element and then one dot for each valence electron that element has, right? And so we have something in group 1, which is our first group in the periodic table. They'll have one valence electron because their valence shell is an s orbital with one electron. And so we would draw, for example, potassium with one dot, showing that it has one valence electron. If we move over to group 2A, we would draw the Lewis structure with calcium with 2 electrons. And we'd draw these electrons unpaired until we got 4, and then the 5th one would have to pair up. If we move over one group, we have a boron with group 3A, so we have 3 valence electrons, 1, 2, 3. And these are the main groups, so we're disregarding the transition elements there. Group 4A, we have carbon and silicon and so forth down the periodic table. They have 4 valence electrons, so 4 dots. We go over to 5A, for example, nitrogen has 5 valence electrons, so we have 5 dots. Oxygen, group 6A, has 6, so we have 6 dots. And then the halogens, for example, fluorine has 7. Oh, looks like a little error there. This is actually neon, our noble gas, and they have 8. Right, so they have 8 valence electrons, and that's what again makes the noble gases so stable. If we look at something like chlorine, right, it's a halogen, so it has 7 valence electrons. And if we put another chlorine over here, it also has 7 valence electrons. But we want to have 8 valence electrons, and so each of these dots represents a pair of this is a pair of electrons, a pair. These are single electrons. If 2 chlorine are next to each other, then they could share these 2 between them, and the sharing of those 2 electrons forms a bond. So we would replace these 2 dots that are between them with a straight line representing the 2 electrons they're sharing. And so this would be what we call a bonding pair of electrons. And this would be a lone pair out here because these ones are not being shared. And so in this configuration, this chlorine atom here, it has 2, 4, 6 electrons, and it's sharing these 2, so they think they both are around it. So it thinks it has 8 electrons, and it's happy. This chlorine has 2, 4, 6, and then it's sharing that pair, and it thinks it has 8, so it's happy. And that's one of the reasons when we were looking at what elements were diatomic, meaning that there were 2 of them together naturally. The halogens were all diatomic because they have this configuration where if they're with another of their same type, then they can share those lone pairs and have a bonding pair of electrons. Right. And we can expand this by looking at larger molecules, right? So if we had something like CH4, we could predict what the bonds are going to look like in that molecule based on the Lewis structures and this set of rules over here. So the first rule we have to follow is we're going to find the total number of valence electrons. Second, then we're going to decide who the central atom is and draw bonds between the atoms and subtract 2 electrons for each bond. Then we're going to assign leftover electrons to terminal atoms and assign remaining atoms to central atoms. Then we're going to check to see if everybody's happy with that arrangement. So to begin with, what we need to do is figure out how many valence electrons, right? So carbon is here in group 4, so carbon has 4 valence electrons. Hydrogen is in group 1, so it's going to have 1. So each one of those hydrogen atoms is going to bring 1 valence electron. So we're going to have a total of 8 valence electrons to share. And that's what we're trying to do. We're trying to take these 8 electrons and share them amongst these 5 atoms to make sure everybody sees as many electrons as they want to see. So hydrogen, its outer shell is that 1s orbital, right? And so that s orbital can only have 2 electrons, so it's happy once it has 2 electrons. And so our second rule is to decide the central atom. So the central atom is the least electronegative atom usually, but hydrogen cannot be the center atom because it only wants to form 1 bond because it can only have 2 electrons. So if you can only form 1 bond, you can't be in the center of anything. You have to be on the edge. All right, so we're going to take our carbon and connect him to our 4 hydrogens. And remember, each one of these lines represents a pair of electrons. So inside of here are 2 electrons. Inside of here are 2 electrons that are being shared. 2 electrons here, and 2 electrons here. Right, so we've used 2, 4, 6, 8 electrons. So we've given out all 8 of our electrons, and we have 0 electrons left. Right? And at this point, then we can disregard these other steps because there's no extra electrons to give out. Right, and so then we have to figure out, is everybody happy with this arrangement? So hydrogen now thinks it has 2, this hydrogen thinks it has 2 electrons, this hydrogen thinks it has 2, this hydrogen thinks it has 2, so all the hydrogen are happy with this arrangement. This carbon thinks it has 2, 4, 6, 8 electrons around, so it's happy with that arrangement as well, so that would be the Lewis structure. All right, so let's try another molecule to do the Lewis structure. So say we have a NH3, right? And we need to do the Lewis structure for that. So our first step, again, is always going to be to find the number of valence electrons. So we have 1 nitrogen and 3 hydrogen, and so we have 5 valence electrons from our nitrogen. Each hydrogen is bringing 1 electron, and we have 8 electrons. All right. So our next step is to decide who the central atom is. Hydrogen can't go in the center, so we'll put nitrogen in the center and set ourselves up like that. Now it says subtract 2 electrons for each bond, so 1, 2, 3 pairs, so that's 6 electrons we have to get rid of. We have 2 electrons left. Now we're going to assign leftover electrons to the terminal atoms, but hydrogen can't have any more electrons. So then we're going to assign remaining atoms to the central atom. So we're going to put that last pair of electrons right up here above the nitrogen. And so our final step is so we're going to subtract those 2 electrons, sorry. So that leaves us with 0 electrons left. Now we're going to check to see if everybody's happy, right? So this hydrogen thinks it has 2 electrons. This hydrogen thinks it has 2 electrons. This hydrogen thinks it has 2, so all the hydrogen are happy. The nitrogen thinks it has 2, 4, 6, 8 electrons. So again, the nitrogen is also happy. So that would be our Lewis structure for NH3. So let's look at a couple more here just to get some more practice. So we take H2O. Right, step 1, find the number of valence electrons. So we have 1 oxygen, 2 hydrogen. So oxygen is in group 6A. It brings 6. Each hydrogen brings 1 electron. So we only have 8 electrons again to disperse. So oxygen has to go in the center. We connect the other 2 by bonds. So there's 2 electrons here and here, so that's 4 electrons. So we still have 4 electrons left. Then we assign them to the terminal atoms. Hydrogen can't take any more, neither can this hydrogen. So then we're assigning them to the central atom. So we have 4 more, so we put 1, 2, 3, 4 electrons. We have 0 left. Now we have to see if everybody's happy with this arrangement. So this hydrogen sees 2, this hydrogen sees 2, this oxygen sees 2, 4, 6, 8, and so it's happy. I neglected to show you this other way of trying to piece these things out. So if we just drew the Lewis dot structure of hydrogen in the middle, and then oxygen with its 6 valence electrons, and then another hydrogen with its 1 valence electron, you can kind of look at that picture and say, well, this means these two would form a bond, and these two would form a bond, and then we would have ended up at the same place. So you can use these Lewis dot structures to get an idea of what they're going to want to do when they form a covalent bond. Right, carbon has 4 dots around it, so it's going to want to form 4 bonds. It needs to share 4 electrons. Nitrogen has 3 unpaired electrons in that scenario, so it's going to want to form 3. Oxygen has 2 unpaired, so it's going to want to form 2 like it did in this scenario here. The halogens have 1, and so they want to form 1 bond like they did with the chlorine that we looked at earlier. All right, so let's see something we haven't seen yet. So say we have a CO2, right? Carbon dioxide. So first step is to find the number of valence electrons. So we have carbon and 2 oxygen. Carbon has 4 valence electrons. Each oxygen has 6. So remember, carbon's in group 4A, oxygen in 6A. So that leaves us with 16 electrons to share. So we're going to put someone in the center. Carbon is the least electronegative, so we're going to put carbon in the center, connect them to the 2 oxygens, and that used 4 electrons, 2 for each bond. So we still have 12 electrons. Each oxygen, so the next rule is to assign them to the terminal atom. So each oxygen can take 6 more electrons around it. All right. So now we've used our 12 electrons. We have 0 more electrons, right? And now we're going to see if everybody's happy with this sharing arrangement, right? So oxygen sees 2, 4, 6, 8. It's happy. This oxygen sees 2, 4, 6, 8. This carbon sees 4, right? And so it already had 4, so it's really not sharing any electrons. So to make it share more, this is where we start forming multiple bonds, where we're sharing more than 1 pair. And if we're sharing 2 pairs of electrons in 1 bond, then it's a double bond. If we were sharing 3, it would be what we call a triple bond. And to form that double bond, we take this pair that oxygen is holding to itself, and we move it here so that both oxygen and carbon can see it. Right? And when we move that pair there, we now have a double bond. Right? And so we have 2, 4, 6, 8. Oxygen still sees 8, but now carbon can see them, but carbon can only see 2, 4, 6. So we have to do the same thing over here by moving another pair into this position here. And now we have a double bond here as well. So now carbon sees 2, 4, 6, 8. Oxygen still sees 2, 4, 6, 8, 2, 4, 6, 8. So everybody's happy once we have those 2 double bonds in there. But we should always avoid trying to form double bonds and triple bonds if we can share our electrons without getting to that point. That's the best approach. So not everything